Hi, I'm Colin. I'm a VP and Distinguished Engineer at Amazon Web Services. And today I'm going to talk about a topic I actually work on almost every day at AWS, which is how we build and operate systems in ways where we don't have access to the data. And we provide customers with confidentiality for their data, but at the same time can provide them with these advanced managed services that are doing operations on their data. And we're going to cover material that we've never talked about publicly before, but this material is the kind of material we get into when we're having conversations with customers and their compliance authorities and regulators as they're trying to achieve compliance and regulatory compliance. And whenever we talk about this topic, I have to give some small disclaimers. The first is that compliance authorities and regulators and customers typically like to review architectures one by one and dive into all the details. And there's no simple, fixed recipe that's, use this and you're going to be compliant. It always takes diving in. So don't take anything that I'm going to go into today as, the simple one stop to achieving compliance or anything like that. And if you have conversations with your regulators or compliance authorities, the AWS compliance team can help you with that. And then the second little disclaimer is, just naturally as we cover this material, we're kind of thinking through threat models that are kind of like movie plot threat models, right? We're talking about risks that aren't very likely, but are, kind of particularly interesting, right? We're talking about risks of, imagine if there were a rogue operator or if there were some kind of, internal systems issue that could lead to data access. And, as an organization with a mature approach to security threat modeling, we have to think about risks that are as advanced as that, but that doesn't mean that they're likely, or that the fact that we're designing for those risks mean, we think that's something that's going to happen. Hopefully that all stays in the realm of movie plots. So the place I'm going to start is just a really simple example that I think gets home our overall approach to customer data and the confidentiality of customer data. And that's what happens when you call AWS support, right? So if you've got a problem or an issue with an AWS service that you're running and you need some help with it, you can call our AWS support team, and they are motivated every day to help people. That is what they live for. They measure their success by how long it takes to get a customer going again. Customer has a problem that's always frustrating. They want to fix that problem and move on as quickly as possible. And at AWS, AWS support personnel, they don't have any special privileged access to your customer data, right? They can't log into an EC2 instance as you. They can't go see your data in S3 or anything like that. And that's always been true for how we operate AWS. But I can remember a time in industry when, different organizations, different parts of the industry, support personnel typically would have special access. They'd be able to just go in and see your accounts and see your details and so on. And often even sometimes just fix things for you, right? And that can be very helpful, right? That can mean people fix your problem faster, right? Which is very satisfying. But in today's environment, that's just not the kind of security world we could all have, right? We all expect much stronger controls around our data and how it's accessed. And so even though we really want to be able to help people as quickly as possible, AWS support personnel or any AWS operator, if they were trying to help you, if they needed special access to your data, the only way to do it would be for you to grant them that access very explicitly. And even then, they wouldn't want it, right? In most cases, most people have been trained to feel like that's not something they should do or get close to. In fact, AWS support do have some limited access to be able to list some metadata and so on and see what services you're using and be a little bit helpful and so on. They have what's called a service linked role that helps them with that. And you can actually see there's a published managed policy for that describes everything they have access to. It's all out there. You can see what they can access, and many times you can see any access that happens in like CloudTrail logs and so on. And anything beyond that, and that can be revoked at any time, right? Customers can decide to deny that access to you just by having their own policies that say no, don't grant that permission. And so that reflects an internal approach where we kind of see customer data as radioactive to us, right? And that's a word I hear used a lot, right? From whether it's individual service teams or all the way at the most senior levels of AWS management. We basically never want to see or touch customer data directly, right? It's just not something we want to see. If there's even a hint of us getting close to customer data, we want to flag a lot of concerns and stop that as quickly as possible. It's just not something we want to be near or close to at all. And so we build shielding so that we can't see or touch customer data directly, right? And the shielding we build, a lot of the tools and systems that we've developed for this are actually the same tools that we can give to you, right? And I'm going to talk through how you can build your systems in ways where you don't have access to your customers' data, because that's an increasingly prominent trend, an important part of how security is evolving in our industry. So the first part of this shield is kind of very traditional security techniques that you'd be used to and familiar with. So, for example, whenever I have to log in or administer any kind of or use any kind of internal tool, I have to authenticate myself using multi-factor authentication. And then we've got a lot of best practices around how we manage physical security, physical access to our buildings and data centers and so on. And we've got advanced monitoring and detective controls that are looking for any aberrations or suspicious patterns of activity and so on. And this is the kind of stuff you'd be used to, although I suspect we're quite evolved on this path. And but I'm not going to talk too much about this kind of shield material. The other shield material is kind of baked into how we build and design our systems, and the approaches we use to kind of ring fence data from us, so that there's no way we can just access it or inadvertently come across it in any kind of haphazard way. And we use tools and techniques you'll be familiar with. And as I talk through them, I'm going to highlight ways you can use them for yourselves. So this is all built on top of, or our whole approach is built on top of the principle of least privilege, which simply says that nobody should have access to something unless they really need it, right? And going a little further than that, they should really only have access for as long as they need it, right? And they should prove that it's needed. And so to the maximum degree as possible, we always want to absolutely minimize the surface area of any data that's exposed, how long it's exposed for, where it's exposed, and so on. And the biggest and kind of most important way we do this is actually using the AWS Identity and Access Management System, the IAM service. So the IAM service is the service that authenticates every AWS web request. So when you as a customer call AWS, you're actually making a signed, secure signed request using the SIG-v4 protocol. And then the IAM system authenticates and authorizes that request, right? Figures out who you are and looks at security policies and so on to vet that you should actually be allowed to make that request. And if you are, it lets you, and if you're not, it doesn't, and so on. And we actually use this internally as well, pervasively. Access between AWS services is mediated by the IAM service. And so we're using principles and roles and policies and all of those concepts that you're familiar with internally too. Now, we didn't have to build it like this. We could have built it so there's separate authorization systems internally, or even that it's just wide open, right? But that's not what we wanted. Instead, we have the IAM service everywhere. And all of that access, all of the access between services is reviewed on an ongoing basis by AWS Security and AWS IAM. So kind of independent from the service teams themselves, we've got these two specialist teams who are constantly looking at, any internal access. Is it appropriate? Can we scope it down? Are there ways we can limit it? And that service is also ring fenced internally, right? So the IAM system is considered a high security system. The keys and principles and material that are in that system are obviously very important, and they are highly guarded and protected. And people don't have access to those systems. But because we're using the IAM service itself internally, and because it's a service that our customers are themselves familiar with, that allows us to put transparency and consent kind of very front and center to our approach, right? As we publish the internal policies that are being used, so that customers can review, like, here is the level of access that service A has to call service B on my behalf. That is visible. It's in our documentation. We actually publish change logs too. So anytime we're adding or removing capabilities, because our services evolve over time and we add and remove APIs and so on. Sorry, we don't only add APIs. That's visible, and people can see that those changes are appropriate and make sense. And customers can also, veto this. Customers can write their own policies that override this. A deny will always win. And so if a customer decides, even though I'm using service A and it needs to access service B on my behalf, I'd actually not like it to, they can write a policy that will break that effectively. So consent is front and center. And IAM is a very powerful system, right? It's got a lot of amazing capabilities. It's incredibly flexible, lets you write very, very powerful security policies to achieve, extremely advanced postures. But that can be intimidating and confusing and a lot to understand. So we actually also have tools that try to deliver simplicity to be able to wrangle that, power. And Access Analyzer is a great example of one. We actually use the IAM Access Analyzer ourselves to constantly baseline the permissions that we're using between services and teams internally. If you're not familiar with Access Analyzer, I highly encourage you to check it out. But basically, you can take complex policies and really give you very simple answers, like just tell me who can access what. And we use that ourselves, and we have that integrated in an automated way into how we manage those policies internally, so that we can vet those simple questions too, and we can check, okay, there's no case where this service can just inappropriately access too much data and so on, right? Because obviously that would be dangerous if there were some kind of issue or bug or something like that. And then we actually go beyond this. So although we have these managed policies which describe, here's how service A can access service B on your behalf, in many cases, we actually want to go further and say, well, if it's still, we don't just want it kind of sitting around that, service A could just go access service B on your behalf. That doesn't feel like true least privilege, minimal scoping. So we built this capability called forward access sessions, where IAM itself actually maintains a cryptographic chain of custody. That means that on behalf of access, where service A needs to do something with service B on your behalf, can be for a limited point in time, right? For a limited duration. And the way it works is kind of something like this. So imagine you're using S3 and server-side encryption, which is very typical, but you're keeping your key in KMS, right? And so whenever S3 needs to encrypt or decrypt your data on your behalf, because that's what the feature is, it obviously needs to be able to access your key that's in KMS, right? And one way we could have built that is, okay, S3 just has access to your key whenever it feels like it, right? But that's not quite how it works. Instead, what happens is your customer call comes into S3 and is authenticated and authorized by the IAM service. And the IAM service actually provides S3 then with its own cryptographic token that has a limited duration in time that allows S3 to access KMS on your behalf. And IAM is enforcing that chain of custody, independent of S3 and independent of KMS. And so it kind of asserts and proves to KMS that, KMS can go, I'm going to give this key to S3 because I'm cryptographically certain that the customer recently called S3 and had a legitimate request that the IAM service considered, authorized and so on. And we use this capability, quite broadly. So we use it whenever we do server-side encryption, as we saw in this example. We use it in many cases when services need to launch VPC private links, right? So a service, when it's launching a private link, typically needs to, add an ENI and do some things in your VPC, and it's acting on your behalf. And that'll use forward access sessions, or very similar with VPC transit gateways for the same reason. AWS CloudFormation, when it's acting on your behalf, typically uses forward access sessions too, and the new AWS Cloud Control API is another example. And we have even more nuanced examples. So EC2, for example, when it's accessing your EBS encryption key, actually does it via KMS grants. So there's like another level of, again, where a KMS key grant is used in another way to minimally scope things. And if you're really interested in fine detail of how we can get to very, very minimal scopes for operations, I'd encourage you to look at that example separately. I'm not gonna dive into it too much here. This is all powered by IAM and the SIG-v4 protocol, which is cryptographically authenticating a request, right? And can provide these kind of transitive cryptographic tokens that can then be used to act on your behalf. But there are other ways in which that protocol is also designed to be truly minimally scoped and achieve least privilege. I think a great example of that is that, in order for us to authenticate your request, we need a key, right? The IAM service needs a key to go and check whether it matches, what your key is. One way we could have solved that is simply to, put the key in the request as like a bearer token or a password approach. But that's not what we did. Instead, the SIG-v4 protocol uses this amazing scheme of derived keys. And it actually derives, so on the customer side, the customer, when signing a key, so the SDKs and utilities do this for you, so you don't have to think about it. What they're actually doing is they derive a key that's unique for like that service in that region on that day. And that's the key that they use to sign the request. And so on our side, when IAM's verifying your request, it actually only needs a key that's specific to that region, that service, on that day, right? And that means if there were ever some kind of bug or issue in our system where somehow that key ended up somewhere it shouldn't, right? It's still extremely fine-grained and minimally scoped. Simply cannot be used in a cryptographically verifiable way to make requests to any other service or in any other region or on any other day. Right? So extremely minimal scope. And we're going further than that. We recently launched the SIG-v4a API for IAM, where we actually now use public-private asymmetric cryptography, which is a bit more expensive in not money or dollars, but just in terms of CPU time, to authenticate requests. And that actually goes a level further again, because it means all that's needed on the AWS side is a public key, right? And that public key, if that were somehow disclosed or ended up somewhere it shouldn't, simply can't be used to sign a customer request, which is pretty cool, right? Very, very minimal scoping. We also pay a lot of attention to detail to how we authenticate our own access to systems, right? So in general, our philosophy is that systems should be hands-off, and people should really not be logging in or have any general purpose access to systems. Now, part of that is we're just at a scale where we just have way too many systems that you could ever try to manage by hand. Just a daunting number. But it's important for security too. But for some systems, if an emergency occurs or something truly unpredictable, we have break glass mechanisms where, okay, we can access those systems if needed to do some kind of recovery action. Typically that access still, just for those reasons of scale, will have to go through automation. There's no way someone can literally type commands or log into a huge number of systems. But whatever way it's accessed, all that access is thoroughly and robustly tracked and recorded, and in many cases requires multiple people to approve things before they'd actually be able to even access the system. And so there are important mechanisms there that are making sure that any access that ever has to happen, even in an emergency, are appropriate and don't in any way lead to disclosing customer data or getting close to customer data. So that's these are all techniques you can use yourself. It's using access control systems or the IAM system itself, which you can use via API Gateway or other services, are great ways to limit access to data and to systems. But we don't stop there. So the next approach and the kind of next way in which we build our systems to make things manageable is that we use cryptography to minimize the surface area of data that's exposed, right? There are times where we just have to get customer data from A to B, and it has to go through several systems. But as a simplifying measure, as a nice architectural simplifier, we just encrypt that data as we're transporting it around, and we transport the keys separately so that we don't have to think quite as hard or worry quite as much about the level of access to that data as it's being transported. And this is called end-to-end encryption. And this is a great go-to technique. So for example, when we're moving EBS keys within the EC2 system, there are just various parts of our system it has to go through to get from KMS to all the way where it's somehow attached to your instance and can actually encrypt and decrypt your EBS data. Throughout that whole process, that key is actually encrypted, right? So, and the ends of that end-to-end encryption are kind of KMS on one side, so that's where the key kind of starts and lives and resides in a durable way. And the Nitro system, which we'll talk more about later, which is where your key is used, right? And so those systems obviously need access to your key, right? And those are very high security systems. In fact, both of those systems, they don't even have emergency mechanisms for people to log in or any kind of general purpose access. And they've got all sorts of controls around them, as we'll see later, for making them very high security systems. But the systems in between, right, because they only see an encrypted copy of the key as they're transporting it around, they can have a different risk profile, right? They don't quite have to live in that world, which is a very nice simplifier. And it means, if there's any kind of issue in those middle systems, all that they ever have access to is an encrypted, useless copy of the underlying key, which is great. Other examples of this kind of end-to-end encryption in action. So SSH is a great example of this. So we know customer SSH public keys. We have to, and that's part of when you launch an EC2 instance, your public key can be attached to that instance, and that's how you log into it. But we have no copy of the customer's SSH private key, just none, right? So even though we're transporting the public keys around, we have no ability to log into the EC2 instance or way to access it, which is nice. And that security is completely end-to-end between the customer and where they have their SSH key and the EC2 instance, and secures their data not just from us, but like from any party in between, right? So typically when you're SSHing to your EC2 instance, you're going over your Wi-Fi network, and then maybe through an ISP, and then the AWS network, and so on. And none of those networks can decrypt your data, right? You've got end-to-end security in between, so it's a great security simplifier. Now you can extend that kind of client-side encryption, where you've got the key, right, like your SSH key, to a more general form, where you can just encrypt your data before you ever send it to AWS or anybody else, right? We have tools and utilities to help with this approach. We've got the general purpose AWS encryption SDK, which can help you do this for pretty much any kind of data. And we've got specific encryption SDKs for services like S3 and DynamoDB and Nitro Enclaves. And with these systems, right, you can encrypt your data and only send us the encrypted data. And at that point, we're completely out of the equation. We're storing your data. We're in charge of making sure it's durable. You're having us solve that problem for you, but we just have no access to the data whatsoever, even in a theoretical sense. Now, this comes with that comes with great power, but it also comes with some downsides. So one downside of that approach is, well, you have to do all the encryption, right? Another downside is, once you've uploaded that data, it can't really be searched or indexed, or you can't do advanced things on that data because all they have is, the blind encrypted copy, which is deliberately not very useful. And another downside is, well, you have to manage all the keys. But it turns out many of our customers, we can help them solve some of those problems still, even in this world of using client-side encryption. So our key management service, AWS KMS, we've actually architected it in a way where it's a multi-party system, which essentially means none of our operators have exclusive control over the system. It always takes several operators to do key actions on KMS, like bootstrapping it or starting it up and so on. And it's got and it's ultimately backed by tamper-evident hardware security modules, which are again another example of a multi-party system because those are built by an independent party, and together these properties mean that we don't have access to be able to meddle with KMS and have it, tell us what a key is or do things that customers wouldn't be comfortable with. And we've seen customers, who decide, well, for their risk profile, they really want to use client-side encryption and only give, AWS a copy of the encrypted data, but they're still comfortable using KMS because of this advanced posture that it has, and they can still use it for their key management, which is great. And then they can get some great benefits. So for example, because KMS is an automated system, if they want to instantly revoke access to things, they can just, kill an AMS key grant and so on, and the access is gone, right? And so they get some important security benefits that way. And then another example is, well, we can take over doing the encryption for you, even if you want to manage the key. So for example, Amazon S3 supports server-side encryption with customer-supplied keys. You can have them come from KMS, or you can even supply the key, when you're uploading the material. And you might look at that and you might think, well, what's the security benefit? AWS has access to the data, has access to the key at this point in time, But the thing to realize is that exposure to the key is temporary, right? We have access while we're encrypting it. But after that, or after a time at least, we no longer have access to the key. And so if you want to revoke or, cryptographically shred the material, you can just erase your copy of the key. And since AWS no longer has a copy of the key, no longer has any way to access the data. Now, this I've seen customers use this to achieve compliance goals. And if you're in that category, this is definitely an area where we'd want to go through all the fine print and just make sure that all the longevity of the individual key caches and so on all line up with whatever your requirements are. But it's still a pretty cool capability. But the main way we use kind of end-to-end encryption is actually as defense in depth, as kind of a secondary control. So even though we have extremely strong, robust physical security of our systems, we actually encrypt our network traffic too. So we encrypt every link that is out of our physical control, including all the links between buildings, AWS buildings, data centers, regions. And that's done at a very low level with very strong encryption, typically AES-256 or optical layer encryption. And it's just always on, right? And that's just our AWS Lever network encryption. Look up Lever if you're curious for more details on that. But then we go beyond that again, right? If for our modern instance types that support it, we also do VPC encryption, where all the traffic between those instances, whether it's the same or different customers, whether it's the same or different VPCs if they're peered, all that traffic is also encrypted by the AWS Nitro system. And all of this traffic is also not just encrypted, but anonymized, right? Which is important. There are many approaches to encrypting network data where you encrypt the data, but it's still clear whose data it is because the IP addresses correspond to a particular customer or some other identifier and so on. But actually, we took the time to design it in a way where even that information is anonymized, and we built it in a way that's privacy preserving because we wanted the system to work even if somebody was interested in just seeing, well, how much volume is somebody moving around, somebody might be interested in that. And so we wanted to make sure things like that didn't work. And this kind of approach of using cryptography for preserving privacy is increasingly important. I'm not going to talk too much about it today, but if you are more interested in it, my colleague Joan gave a great talk at last year's reInvent. It's up on YouTube, where you can learn about privacy preserving encryption techniques that are used to anonymize data sets that are used in machine learning and AI, and all the great ways in which our personal information can be protected, but still interesting things can be gleaned from those, which I think is pretty great. Okay, but what about compute, right? So we've talked about how we secure data as we move it from A to B, and how we ring fence our systems. But at some point, we actually have to be able to operate on the data, right? Which means having some system has to have access to data, right? And this really gets into our compute systems and how those work. And so there is a form of encryption that can help with this. It's called homomorphic encryption, where it's been an emerging area of research, but essentially it's a form of using cryptography where you can have encrypted data sets and you can still perform useful computation on them. And in fact, this is now general purpose. You can perform any computation on any data using homomorphic encryption, right? Kind of in a very like Turing complete sense, you can build a computer that uses homomorphic encryption. And this is something, we're at the forefront of. We have teams that work on this, and as research we participate on. But the big caveat is that it is incredibly slow. Even the most advanced and performant approaches to homomorphic encryption typically allow you to run, what would often take a CPU, nanoseconds, will run in milliseconds to seconds using homomorphic encryption. So many, many orders of magnitude slower. And so it's not generally a technique that today can be applied to, general purpose applications and so on. It can be used in niche areas. If you've got a very small operation that needs to be done in this way, that is something that can be done. But for the most part, that's not key to our approach to how we secure computation. Instead, we use our AWS Nitro system. So the AWS Nitro system is the underlying platform that powers our modern EC2 instance types for quite a while now. And the kind of foundational tenet, the number one design principle of the AWS Nitro system is that we wanted to provide strong isolation between AWS as the customer. Our second tenet was that we wanted incredible performance, but we were never going to trade that off for security. It's by far the most important thing we were designing for. And a great example of that is the AWS Nitro system. The way it's built is that we've actually put a machine inside a machine. There's a dedicated Nitro card that is physically separate from the hardware running customer instances and accessing customer data, where with its own dedicated CPU and memory and hardware security chip is running the vast majority of our virtualization. So our virtualized network stack, our virtualized storage stack, our own security management, monitoring, and so on. This all runs on a dedicated Nitro card, which is separate from the customer hardware. So if there's a bug or issue in these systems, it's not even on the same hardware that the customer is running on. In the case of non-metal instances, we do have a small, thin hypervisor running on the same hardware as the customer, but it's a tiny, small surface area kind of a system. And we built Nitro in a way where we just have no operational access to the AWS Nitro system. There's no SSH, there's no general purpose login of any kind, not even for an emergency. Instead, every operation is done via secure, encrypted, strongly authenticated APIs. So we've got little microservices running on Nitro, and that's the only way for us to do anything is to ask one of those Nitro microservices to do something. And the only way to get software onto Nitro is to go through our code review and security review and testing and then deployment processes. And those processes involve, quite a number of people. And at every stage, we're vetting that whatever operations we're pushing out to Nitro are safe, and that they don't disclose customer data and couldn't disclose customer data. Even the debugging features that we build are designed in ways that can't possibly disclose customer data. So if we have to debug a networking issue or a storage issue, those debugging tools might let us see, say, some aspects of a packet, but never the customer data or anything like that. And the Nitro system also runs in a dedicated, isolated network. So our access to it is through this network that very few tools and people have access to, and has no general internet access or anything like that. And we've been extending this model to other systems. We really like this model where you design and build a system from day one where it just doesn't even need operators. It's great for security. It's also great for stable operations, right? We can give, this lets us deliver some really powerful forms of isolation. In fact, with our Metal instances, customers just get the dedicated hardware, right? They get the whole system. Our stuff is running on the Nitro card, and there's just strong, all the way up to physical separation between those systems. Great example of this is our Mac 1 instance types, right? Which is clearly, a Mac machine, right? That we're not running code on. And that's where the customer gets to run their system, and our stuff runs on Nitro. And then on virtualized instances, those instances are all fully isolated from one another. So one instance can't read another instance memory or anything like that. And they're also isolated from the Nitro hypervisor. So the Nitro hypervisor, which kind of manages those instances, actually has isolation between the hypervisor and those instances. And that isolation is actually backed by hardware. It uses the hyper-virtualization extensions that are built into CPUs. And we're very deliberate in what we'll share, ever. So instances, for example, never share CPU cores at the same time, or L1 and L2 caches and so on. And that's because we want to make sure that our systems are robust, even against emerging side channel research and so on, right? We want to have an extremely strong and robust level of isolation and protection. And so what all this means is the AWS Nitro system has from day one provided what's kind of now called confidential computing, where we as operators of AWS and the Nitro system, we just don't have access to customer data. There's just no way for me to read it or access it. And we think this goes further than and complements kind of approaches based on cryptography. So earlier, where we used cryptography to protect information as it's kind of moved from A to B, cryptography works great when the data is not changing. Right? When I've got some data, I need to move it from A to B, but the data is not changing as it goes. When data changes in real time, cryptography often isn't the best line of defense, because those changes can still be visible. So even though the cryptography can't be broken open and you can't read the data directly, you can see which parts of the data are changing and when, right? Because that can't be hidden by cryptography. And often those patterns of changes are enough to reveal details about the information. And that's why we see emerging side channel research that can use that property to break systems that are just dependent on cryptography. So we like to have that hard isolation in front of cryptography. Now we do use cryptography too as an additional defense in depth. We have it included in Graviton 2, for example, where we encrypt all of the memory. Another great thing about Nitro is that because all of this just shows up as a new instance type, you don't have to change or modify applications in any way. You can just run your regular application on the AWS Nitro system and get all these benefits where there's no way we can access your data. which is, I think, pretty cool. Now, that's how we isolate ourselves from AWS customers and their instances. But we're actually giving customers now capabilities where they can do this themselves and build systems where they can't access their own, compute systems. And so this is where Nitro Enclaves fits in. And so in Nitro Enclaves, you launch and run an EC2 instance as normal. And then from that instance, you can launch and run a Nitro Enclave. And that actually shows up as a virtual machine that's running side by side with your instance. And the isolation is powered by the Nitro hypervisor. So the isolation between these two is as strong as the isolation between any two EC2 instances. The EC2 instance can't see inside the enclave, and vice versa. And they're highly isolated by default. There's no storage, there's no network, there's no interactive access. And so the enclaves just really strongly emulate our model of very, very small surface area. And all the connectivity between the two is that there's a virtual socket, which is kind of like a virtual serial cable between the EC2 instance and the enclave. And that's how all communication happens in and out. We've got helper agents and utilities that let you build applications that run inside the enclave and communicate with the outside world in a very limited way if needed to get encrypted data in and out using end-to-end encryption, as I explained earlier. And so you can kind of glue together all these techniques to build a system where the EC2 instance in the middle and your operators and administrators, they just have no access or visibility of what's going on inside the enclave or of the data that's being sent into the enclave, which is great. We've got cryptographic attestation so that you can get the same kind of properties we have of being sure that any software running on the enclave is the correct secure software that only does what you would like it to do, right? So the way that works, typically when your enclave application starts up, it generates a local public-private key pair, right? And those live and die with that enclave. The private key never leaves that enclave, ever. But the enclave does supply the public key to what's called an attestation service. So it basically talks to Nitro under the hood, and Nitro gives back this attestation document that says, we're going to give you this cryptographic evidence that this is the Nitro Enclave running. Here's its checksum. Here's the application that's running on it. Here's when it was launched. Here's its role. All of these kinds of things. That's signed by Nitro, so you can cryptographically verify it. And because that has the public key in it, right, you can give that attestation document to external services, and they can encrypt material using end-to-end cryptography, like we saw with SSH, like we saw with end-to-end encryption, that can go through your architecture in your system and only be decrypted by the Nitro Enclave. And only your Nitro Enclave has access to that material, and your administrators, operators, and so on, they can't access your Nitro Enclave. And so you can get all the benefits of building an architecture in that way, just like we've built Nitro to isolate our customer data from ourselves. So that's the key parts of our approach. That's kind of how I think about our architectures, at least, to how we glue all these parts together so that we get systems that work well together. But I can also have pretty robust statements about our systems and pretty robust properties in our systems where I know, even in these various components, they just don't even theoretically have access to customer material because we've got these strong security systems that are backed by, provable cryptographic techniques, which is pretty awesome. The key takeaways, I hope you take away from this is that systems like IAM, permissions and policy systems, are tremendously powerful. And if you can apply that least privilege principle to every part of your system, you can get an awful lot of benefits. Now, you can layer on top of that encryption as both a primary control, like we saw with end-to-end encryption, or as a secondary security control, as we saw with like network encryption or confidential computing. And that's always worth doing. That can always be helpful. Forgive the pun, but I think another key takeaway is that we can't take away the keys, right? There's just ways where we just don't have access to material. And that's really, really important. And building systems in those ways is important for earning customer trust and important for providing customer trust, right? It's just a great way for us to simplify our designs and be able to stand over these systems. And now we're delivering architectures where you can do the same. You know, you can build your own application and architecture in this way and use things like KMS or Nitro Enclaves to be able to run your own systems in ways where you don't have access to data, which I would love to see even more and more of out there. So thank you very much. It's been a privilege to present to you all. If you'd like to see or read more, there are some more details about how we do IAM and SIGV4 encryption in my blog. Just search for my name and SIGV4 and you'll find that. And otherwise, I hope you got a lot from this talk. Thank you again.